for this is the hold time is 10 seconds, and let's say we take 2 seconds to rise, and we have, let's say, 7 seconds to 10 seconds to fall down. And this peak stress, let's call it sigma max, and let's say this peak stress is about 50 kilopascals. So let's go back to the code. So we need to build a linear equation from time t equals to 0 to t equals to 2 seconds. So if you look at this, it's t equals to 0 to t equals to 2 seconds. We need to ramp up sigma. So sigma is equals to 2 times, or 50 kilopascals, sigma max. So the slope of this curve is 50 kilopascal divided by 2 seconds. So we're increasing the strain. 50 kilopascal divided by 2 seconds is equals to 25 kilopascals per second. So this is the rate of change of stress. So let's say sigma max is equals to 50 kilopascals. Peak stress is 50 kPa, and the time to achieve sigma max, T S max, is equals to 2 seconds. Let's say time to achieve sigma max. So sigma is equals to sigma max divided by T sigma max, or TS max, times T. So now if we plot T and sigma, it will keep increasing forever. Like for we have T equals to 10 seconds, so the sigma will keep increasing for 10 seconds. But just to check that we have what we want, we will plot it. So matplotlib inline. This is used to make sure plot appears in the document, and import matplotlib.plt pyplot as plt. So if we now plot T versus sigma, what we'll see not be in an inline statement, so we'll put the comment on one line below. So you can see as time is increasing from 0 to 10 seconds, the stress is continually increasing from 0 to 50 kilopascals, but at 2 seconds, but it keeps on increasing. That's not what we wanted. What we want is we want it to increase to sigma max 50 kilopascals and then stay at sigma max. So Let's change the code a little bit. So let's say sigma t greater than 2.0 is equals to sigma max. So can't assign to function call, so you need a square braces for this. So you can see now the stress increased from 0 to 50 kilopascal and stayed there. You can't see it here completely because it's coincides with the grid. So what we'll do is we will increase the Y limit of display to from 0 to, let's say, 55 kilopascals. So now you can see that the stress has increased to 50 kilopascals and stayed there for the rest of the 10 seconds. But again, what we want is that we want it to decrease to back to 0 when we reach 7 seconds. So after we reach 7 seconds, we want a constant unloading of the material. So the slope here, so if we want to get the slope at this area, the change in time is 3 seconds. From 7 seconds to 10 seconds, it's 3 seconds. And the change in stress is negative 50 kilopascals. And so what we want to do is we want to subtract 50 kilopascal per 3 second every time step in this region. So let's call that. So instead of hard coding this 2.0, I'll change this to ds max, and I'll say t release equals to 7.0 time, after which we will release the stress. So what we need to do is sigma t greater than t release is equals to sigma minus t minus 7 times t s max no, t minus 7 is actually t release. It's sigma max sigma max divided by 3 seconds. So we don't have 3 seconds anywhere here, so to get 3 seconds we'll say t max is equals to 10.0, and we'll use these parameters ahead of time so that we don't need to remember what it is. So t max, so that we can change, for example, later we can change it more easily, divided by t max minus t release. So now if we save this and plot this data, we have some errors. So we need to add this. So we need to modify only the part that needs to be only the last segment of the data. So if you want to put it in 2 lines, that's what you do. So now we have the time versus stress profile. So we'll label this, label T in seconds, and T stress sigma in pascals. So instead, if we wanted to plot kilopascals, we would have divided by 1,000, and we'd get 10, 20, 30, 40, 50.